Huh? I wish I recorded it. I think it gave you an idea of what we are doing here. Kind of attached back to reality. But anyway, so here's the theorem that basically summarizes what I said about the role of the gradient. So suppose a function f is a differential function. Okay, then the maximum value of the rate of change the maximum value of the directional well, let me pause here before I write and say we have directional derivatives in infinitely many directions. As we are talking about the function on the surface, and so we can point in any direction and calculate the directional derivative. The question is, of course, where we're going to find the maximum value of the directional derivative. So that's what I'm going to write here. So the maximum value of the directional derivatives, and in general to be the operator d sub u of f of x, and I'll put x bar on top of it, I'll talk about it in a second, is given by the magnitude of the gradient and it occurred when this particular u, so we know it's a unit vector, has the same direction as the gradient vector. Okay, so what is that x bar? Well, we kind of generalize it. We are not sure whether we're talking about a one variable function, two variables function, three, or so on. So if in case of three variable function, that will be the x, y, z. Okay, so we can generalize it. If you have a function of four variables, then x bar will be a vector or an array x, y, z, w, and so on and so forth. Okay, so instead of spelling out f of x, y, z or f of x, y, we just write f of x bar, and we are done with that. Okay, so here's an example to go along with this. Suppose the height of a hill above sea level is given by a certain function. So the function will be z equals 1000 minus 0.01 x squared minus 0.02 y squared. Okay, so we have several questions. Well, first of all, we want to know in what direction the elevation changing the fastest if you are at a certain point. So the question is, in what direction is the elevation changing the fastest. If you are at the point, let's say 60 and 100 on the hill. And this can be either feet or meters or your unit of elevation of choice. So we can go with feet here. The next question is, what is the maximum rate of change, or what is rate of change or rate of elevation? Let me change the wording here to rate of elevation. At this point. All right. So let's look at the function that describes this particular hill. Okay, this is probably some kind of artificial hill because it has a specific shape. What is the shape of this hill? If you look at this function, can you tell? In order to figure out what is the shape, set y equals 0. What is it that you're looking at if you cover y? What is this function? Parabola, right? It's the other way around, because if you let x equals 0, you have another parabola. So you have parabola in both directions, so it's a paraboloid. And now, what is the cross section? What is the horizontal cross section? All right? What is the horizontal contour? Well, if you let z equal a fixed value, let's say z equals 0 for sake of discussion, or let's say even z equal 999 or negative 999. No, let's make z equals 0. It doesn't matter. Let's make z equals 1001. So you subtract and you have 1 equal to this. What is this thing? It's an ellipse. Okay. If the coefficient were the same, then it would be a circle. So it's elliptic paraboloid. Okay. So it's not that easy to find in nature, elliptic paraboloid. I'm sure they exist. So, but this may be an artificial hill or something like that. So let's write first that notice that the hill is an elliptic paraboloid. And is it open upward or downward? Well, if it's a hill, it has to open downward, right? And you can see, because you have z, and then you have negative something x squared or negative something y squared. And so that's what will make it a hill. If these two coefficients were positive, then we wouldn't have a hill but a valley, right? Then the paraboloid will be open upward. So it's up and downward. By the way, what happens if we had mixed signs? Let's say the coefficient of x squared is positive and the coefficient of y squared is negative. Hyperboloid, yes. And that, again, we need to check if it's a one surface or two, but depends on well, in this case, if you put z on this side, that will tell you whether it's a one or two sheets. So, but it will be a hyperboloid. All right, so so let's try that it open downwards. All right, so we first need to find the for part A. We know by the theory, we know that the direction that is of the elevation, the fastest rate of change will be in the direction of the gradient vector. So let's find it. So in general, the gradient vector in this case will be, well, before we go there, let's set up a function well, we have z equal f of xy, so before we'll do a little preliminary thing here. We're going to say that f of x is simply negative 0.01 x squared minus 0.02 y squared. So the gradient will be negative 0.02 x minus 0.04 y, and in particular the gradient at 60 and 100 equals negative 0.02 times 60 minus 0.04 times 100. Okay, so I think and this is in the I direction, and this is a vector, so we need to put the I in j. So we have negative 1.2 I minus 4j. And that's the direction where the elevation will change the fastest. Okay? And it's downwards, of course. So, go ahead. X bar is just the array of the variables. If it's 2 variables, it's xy, 3 variable xyz. You must just walked in after I introduced that. It just instead of spelling out the list of the variables, say, okay, we have a variable array. We call it x bar. An array essentially is a vector, but it's not necessarily a geometric vector, a vector that you can describe geometrically. I mean, you can have an array of 10 different items in it. Now try to show a space with a 10 variable space. That's going to be 10-dimensional space. That's going to be tough to draw. Part B, we want to know what is the maximum rate of change. Well, all we need to do is take the magnitude. So actually, let me write the conclusion right here. So maximum, actually let me write it on the next page. So the maximum change of elevation occurs in the direction of the vector negative 1.2 I, negative 4j, or if you like the vector component better is 1.2 comma 4, like so. All right, so this was the answer. Now for part B, what is the maximum rate of change? Well, the maximum rate of change is the magnitude of the gradient vector at this point. So so maximum change or maximum hour c equals the magnitude of the gradient at this point, which is 60 and 100. So it's simply the square root of negative 1.2 squared. Well, that would be positive 1.44 plus 4 squared. That would be 16. So we're looking at 1.44 and 16, 17.44 square root of. And this will be something like 4 point something, 4.2 or I think 4.18. Now, what does it mean, really? It's a magnitude. We know it's downward. Do you know what's the percentage here? %418. Now, it seems to be really high. Isn't it? If you go straight up, what would be the percent of rate, the percent of the rate of change? If you climb up on the wall, 90 degrees, but in percentage, what's going to be? What's going to be the slope? I'm sorry? 1, really? 1 in percent is 100, right? What does it mean, really? The straight wall is undefinable, because what is the slope of a vertical line? Right. So what is 100% rate of change? It's, remember, slope eventually is rise over run, right? You rise as much as you run. So it means that for every, let's say, foot of elevation, you move forward a foot, or it's a slope of 45 degrees. 45 degrees is 100%. 418% is pretty steep. Okay? How steep it is, if you need to build a road, you're not going to take this direction. Okay? Did I tell you last time when we talked about the topographic hill about probably the steepest road in the U.S.? Road in the U.S. street. Yeah, I mentioned that in the honor class. I mean, what do you think when you have a really, really tough climb on the car, on a road? What do you think the percent of the elevation, rate of elevation? It's Lombard, yeah, the steepest one is Lombard Street in San Francisco, and I drove it in 1975. So that was, 2 years ago or so. You were born in 1975? So you didn't drive it in 1975, I guess, but it's really steep. I mean, it's steep, so you sit in the car and you look ahead and you don't see the road, you see the sky. I mean, really, it's scary at times. And guys, 5% is very steep for climb on a car. That's why you see serpentine roads to reduce the steepness of elevation. So this, of course, this is incredibly steep, but it's not straight up. Straight up would be infinity in terms of percent. So, and 100% is simply 45 degrees. Now, if you walk, it's not a big deal if you have an elevation, rate of elevation of 100%. The angle, or whatever the tangent, you do inverse tangent of 4.18 and you get the angle. Inverse tangent of 1 will give you the 45 degrees. He's using calculator. He's going to tell you in a few seconds. You see, we're ahead of you. Yeah, that's 75 degrees. Now, if you climb it by foot, You'll be tired, but it's doable. I mean, think about what is the elevation, the rate of elevation if you climb on a ladder, a step ladder, or something, or a type ladder. That's pretty much 400-500%. Or all right, let me give you another fact.